So very good morning to you all. So today we are going to start with, for the last session, we have gone through one point that is related to the undriven RC circuit. So today we are going to continue with it is natural and forced responses or the response of RL and RC circuit. So what is the meaning of this natural and RC circuit? So whenever we are dealing with this RL and RC circuits, the responses which are obtained from RC and RL circuits are mainly divided into two types. One is known as natural. It is also known as zero input. And second one we have, it is the forced or the zero state response. Okay. This is also a response. So natural or a forced response. So what is this zero input response? See, this zero input response, as the name indicates, input is not applied to the circuit. I'll just categorize the same. Here, the input is not applied to circuit. Okay, and then the response of output, or the what we can say, the output of the circuit is purely due to initial condition. Response is purely due to initial conditions. So here initial conditions are non-zero. So the network is called initially non-relaxed network. It is also known as non-relaxed network. Why it is known as non-relaxed network? Because initial conditions are not zero. Okay, if this type of response is, or this type of response is also known as the natural response. What about the forced or the zero state response? So consider a zero state response is applied to the network and all initial conditions are zero. All initial conditions are zero. So what will happen? Therefore, the response of a network is applied to the input is called the zero state response. Okay, I'll write here all initial conditions are zero. Okay, and the response of a network is applied to input. Response of network is applied to the what response of the network to the applied input is called zero state or the forced zero state response. So since the initial conditions are zero, such network is said to be initially relaxed. Okay, it is initially relaxed one. Next, so in this case, the applied input force for the network to produce the output, and it is also called as the forced response. Keep in mind, this is just a theory part. If they ask you for the theory exam, you must know. That's why I've gone through this point. Next point that we are going to continue with It is a source-free series RLC circuit. Okay, so you must know there is one term which is expected into your what we can say in your theory, that is the RLC circuit. But before that one, we must know what is the source-free RLC circuit. We have already gone through. Source-free means there will not be any energy source associated with the circuitry. And as it is the RLC, now resistor, inductor, and capacitor will be connected into the series. So let us start with R, L, and third one is C. Okay. So for that one, it is IR is equal to IL is equal to IC. It means all the currents are same. Voltage across the resistor, VR, voltage across the resistor, VL, and voltage across the capacitor, we'll call that one as the VC. So let us start with the derivation. So initially, for to define, I just mention it like first point, equation in terms of IL. So apply KVL to the given network. Therefore, it will be VR plus VL plus VC is equal to 0. But we know that what we know, VR is equal to what? Voltage across the resistor. It is IR into R. VL is what? Voltage across the inductor. It is L into DIL by dt. And third one we have, it is a VC. So it is the voltage across capacitor. So it is 1 by C integration of minus infinity to t IC of t by dt. Now let us call this equation number 1, 2, and 3. Now if we put, actually this should be a, let us call this one as 4 instead. Put 1, 2, and 3 in what? 4. We get what we get? We'll get the equation as IR into R plus L into DIL by dt plus 1 by C integration of minus infinity to t IC of t dt is equal to 0. Let us call this one as equation number 5. Okay. So if we go through the figure or the circuitry that we have, and if we check the same, now by referring this equation number or the referring this circuitry from circuit, what we can write, the current across the inductor, capacitor, and a resistor is same. So we want equation in terms of what? IL. So by replacing IR and IC by IL, as we required equation of IL, replace IR and IC by IL. Okay. So to eliminate, okay, before we write, I'll just write the same equation. So your equation will be now IL into R plus L into DIL by dt plus 1 by C integration of minus infinity to t, it is into what? IL of t into dt which is equal to 0. Therefore, now what we can eliminate here in this equation, we can eliminate t. So to eliminate integration sign, differentiate with respect to the t. To eliminate integration sign, differentiate with respect to t. So what will be your equation for now? It will be r into dil by dt plus L into d square into IL divided by dt square plus 1 by C into IL, which is equal to 0. Now, if we rearrange the same equation by rearranging the equation, okay, we get L into d square IL by dt square plus R into dil by dt plus 1 by C into IL, which is equal to 0. So to make coefficient of d square by dt square equal to 1, divide both sides by L. Therefore, what you will get, this is what the final equation you will get, it is d square IL by dt square plus R by L into dil by dt plus 1 by LC into IL, which is equal to 0. Let us call this equation number as, what are the previous equation numbers we have gone through? 5, yes, and this equation we have called it as 6, and 7. Okay, so this is what a second order, this is second order differential equation of source free RLC circuit. This is a second order differential equation for source free RLC circuit in terms of IL. Hope you all have understood the same. Let us go with the next derivation. That is equation in terms of VC. Okay, so let us consider the same equation, and let us consider the equation number. We have written it as the second one, that is the equation that we had, it is VL. What is the equation for VL we have written? It is L into dIL by dt. So we have to express every current in terms of IC, because what we are expecting is we have to identify VC. So let us start with the same. So equation in terms of VC. So consider the previous equation we have gone through. So we have to express every current in terms of IC. To identify VC, put all terms in terms of what? IC. Therefore, what we can do, right? IL is equal to IR is equal to IC. Therefore, IL is equal to IC and IR is equal to what? Again, IC. So let us put this voltage across the capacitor and your equation will be, it is IC into R plus L into DIC by dt plus VC is equal to 0. So now we want equation in terms of VC. The capacitor current IC can be expressed in terms of voltage or the capacitor voltage VC. Therefore, IC can be written as C into dVC by dt. So let us call this equation as 8 and this one as 9. So if we put 9 in 8, we get what we get? RC dVC by dt plus L into d by dt C into dVC by dt plus dC is equal to 0. Therefore, RC into dVC by dt plus LC d square VC by dt square plus VC is equal to 0. Now, by rearranging the terms, by rearranging the equation, we get LC into d square VC by dt square plus RC into dVC by dt plus VC is equal to 0. So to obtain the coefficient of d square by dt square VC equal to 1, I'll just write to obtain the coefficient of d square by dt square into VC equal to 1, divide both sides by LC. Therefore, we get what we get? We'll get it as d square VC divided by dt square plus R by L into d by dt of VC plus 1 by LC, okay, into VC, which is equal to 0. Let us call this equation number as 9. So this is second order differential equation for source free series RLC circuit in terms of capacitor voltage, that is VC. Okay, so this is what for the source free. Now we have to start with the last one, that is driven series RLC circuit. So what is the meaning of this driven series RLC circuit? So let us draw the same. Okay, driven means we will be having a voltage source to drive the circuitry, a resistor, inductor, and a capacitor. Okay, C, L, R. The current, let us call it as I. That is one switch. Okay. Voltage across resistor VR, voltage across inductor VL, and voltage across capacitor VC. Okay. So we have the circuitry. So consider RLC circuit, and the switch is closed at t is equal to 0. What is t? It is time. So we are assuming that initially there is no charge on the capacitor and inductor. After closing the switch, voltage V is applied to the circuit, and thus for t is greater than 0, by applying KVL, we get equation by applying KVL, we get it is VR plus VL plus VC is equal to what? A total voltage V. Therefore, we know what is VR. It is IR plus L into di by dt plus 1 by C integration of I dt, which is equal to V. Let us call this one as equation number 1. So differentiating both sides with respect to t, to differentiate both the sides with respect to t, we get R into di by dt plus L into d square I by dt square plus I by C is equal to 0. Therefore, your equation will be known. It is L into d square I by dt square plus R into di by dt plus I by C is equal to 0. Let's call this one as equation number 2. So this is linear. This is equation 2 is linear second order differential equation with constant coefficient. Okay, now putting d by dt is equal to s in equation 2, we get what we get. L into s square into I plus RSI plus I by C is equal to 0. Therefore, it will be now L into S square plus RS plus 1 by C into I. I is taken as common. Now, by dividing both sides by L, what we get? It will be now S square plus R by L S plus 1 by LC into I, okay, is equal to 0. So this is called a characteristic equation or a auxiliary equation of a series RLC circuit. So this is called characteristic equation or auxiliary of series RLC circuit. Okay. Now, what are the expected things? We have to find its equation. So there are the few terms that are related to the equation. Okay.